Moderate intensity and moderate duration. This type of activity is completed using the lactic acid system. Typical sport is the 400 meters, as you can see in the bottom right image. The fuel is glucose, carbohydrates, or glycogen. The fibers are fast twitch. The waste products are lactic acid and hydrogen ions, and there are no other products. Lactic acid is made in anaerobic glycolysis, where glycogen is broken down into glucose by glyphosphorylase in the muscle sarcoplasm. Then glucose 6 carbons is broken down into pyruvic acid by phosphofructokinase, which is then broken down by lactate dehydrogenase into lactic acid. There's a 2 ATP net gain. RER. RER is respiratory exchange ratio, and in this system it's normally at 1 because you burn carbohydrates during the lactic acid system. As you can see in the right image, when RER is at 1 or above, the fuel uses 100% carbohydrates and 0% fat. And in the left image is my RER from the lactate threshold test that we did at Brighton. As you can see, it is mostly above 1, apart from at the start. So the fuel I'd used was always carbohydrates. Glucose depletion. Glucose is the main substrate for the brain, and low blood glucose, which is hypoglycemia, may also reduce how much oxygen goes into the brain and therefore causes central fatigue, which can lead to a decrease in performance because our brain's not working as quickly, so we can't think as fast. Hypoglycemia is where blood glucose levels are low after glycogen stores have been depleted and before gluconeogenesis starts. An athlete may get some of the symptoms some of them are like shown in the right hand image. Some of the symptoms are shaking, dizziness, sweating, anxiety, hunger, fast heartbeat, impaired vision, weakness, fatigue, headache, irritable. These will decrease performance because you won't either be able to perform or you will drop your intensity. For example, impaired vision, you wouldn't be able to see as well. So something like cricket, you wouldn't really be able to hit the ball. Headache will make you not be able to concentrate on the game, and dizziness you won't be able to focus. Lactic acid accumulation. The effects of lactic acid accumulations are that the enzymes are inhibited and stop working, which then causes muscle fatigue and soreness, which decreases performance because you have to drop your intensity. You can't work as hard as you were before. As you can see in the bottom right image, as power goes up, so does lactate in the lactate threshold test that I did, and it slowly builds up at moderate intensity, as you can see on the middle distance on the top image. Obla starts at 4 mmol, which is the onset of blood lactate accumulation and is where fatigue starts to set in. So as you can see, my Obla was around 180 watts and performance and intensity will drop when Obla starts because fatigue has kicked in. Acidity versus alkalosis. Acidity is where there is more acid present in the blood and other body tissues. It can occur when more metabolic acids like lactic acid are produced. There is an increased hydrogen ion concentration in blood plasma. Alkalosis is where there is less hydrogen ions concentration in arterial blood plasma. Hyperventilation causes respiratory alkalosis, loss of CO2. These both cause a decrease in performance because you start to fatigue more, which means your intensity will drop. Carnes 2006 says acidosis has little effect and can even improve performance. Severe blood plasma acidosis reduced CNS drive to muscle causes a worse performance. So as you can see, normal acidosis can even improve in performance. Alkalosis through soda loading neutralizes the lactic acid built up in the blood and improves the performance from 2 minutes to 10 minutes. It is also called buffer boosting. It appears naturally in the blood and is the body's primary buffering system, so it buffers lactic acid by ingesting lots of sodium bicarbonate before an event. The side effects are vomiting and diarrhea though. Hydrogen ions. Hydrogen ions is the acid in lactic acid, and it interferes with the electrical signals in your muscles and nerves, slowing your reactions down in your glycolytic enzymes and impairing muscle contraction. It is the burn you get during intense exercise. This will decrease performance because you won't be able to react. Your muscles won't react as fast because you have slower energy reactions, and muscle contractions are impaired, so you can't work as hard as before, and your intensity will drop. The VO2 max test. We did the VO2 max test at Brighton University, and on the left image is my results. The blue line is absolute oxygen uptake, and the red line is relative oxygen uptake. As you can see, relative oxygen uptake is a lot higher than absolute oxygen uptake. Along the bottom is the stages. So we did 8 stages. Powers increased 21 watts each time. So as you can see, it gradually increases over the stages. And the VO2 max test determines your body's maximal consumption of energy and the efficiency of your muscles. Glucose ingestion. This is a strategy to reduce fatigue and therefore enhance performance because you're able to work at higher intensity for longer. You can do it through energy gels like in the right hand image, and glucose in glucose drinks like Glucosade. These help to improve performance by raising blood sugar and stopping it getting too low. There needs to be enough glucose so it can be used as a fuel. Glucose is needed in the brain to stop central nervous system fatigue. Carbohydrate ingestion. If a carbohydrate beverage is ingested, then blood glucose and muscle carbohydrate oxidation is maintained, enhancing endurance performance. But fatigue isn't prevented, but stuff like CHO carbohydrate rinsing can activate your sensory nerves in your central nervous system to enhance performance. Lactate buffering. Lactate buffering is the removal of lactic acid, but it relies on the buffering capacity of the body, which weakens the effect of lactic acid and improves performance because we fatigue less quickly and can work at a higher intensity for longer. Hydrogen carbonate ion in the blood, which is produced by the kidneys, absorbs the lactate and forms carbonic acid. It's degraded to form carbon dioxide and water, which are both taken out by the lungs. As you can see in this image, both pre and post training, bicarbonate of soda, which is the method you use to do lactate buffering as I previously described, shows that you're able to work for longer, more time on pre and post, but is much more effective post training than the placebo. Oxygen deficit and EPOC. The graph in the bottom right corner shows oxygen deficit will be larger because there is longer exercise than the low duration, high intensity system or type of exercise, but it's larger, which means that epoch will be larger because there's more oxygen debt to repay because we're working anaerobically for longer, which means we have to borrow more oxygen and means we have to repay more back. Metabolic demands. There will also be a larger slow component lactic acid of epoch present than in the ATP-PC system because carbon dioxide is removed by plasma and carbohemoglobin. It maintains ventilation, circulation, body temperature. It needs 5 to 8 liters of oxygen and can take minutes up to hours. It removes or oxidizes the lactic acid system and it replenishes muscle glycogen stores. Metabolic demand. Metabolic needs the extra VO2 consumed after exercise by organs such as the heart and respiratory muscles. The heart muscle needs oxygen to sustain elevated heart rate and stroke volume. The respiratory muscles require more oxygen to keep breathing rate and tidal volume elevated. Eventually, cardiac output restores heart rate and stroke volume to resting levels. Ventilation is restored to resting levels and temperature is restored to resting levels. Cardiac output is restored to resting levels by heart rate and stroke volume changing, and ventilation is restored to resting levels by breathing rate and tidal volume changing. Gluconeogenesis is the metabolic process which organisms produce sugars for catabolic reactions. The size of the alactic fast recovery is smaller than it is for the high intensity short duration exercise because we also have the lactic acid slow recovery process for this type of exercise because we need to remove or oxidize the lactic acid we've produced during this type of exercise. Also, we need more. This type of recovery takes longer because we need more energy from the aerobic system to resynthesize the ATP and PC stores by sticking the P back on because we've had to use more energy because it takes longer. The alactic fast recovery system takes 3 to 4 liters of oxygen approximately, and 50% of phosphocreatine restored in 30 seconds, 75% restored in 1 minute, and 100% takes around 3 minutes. Removal of carbon dioxide by the lactic acid slow recovery system. As you can see in the graph, the more recovery time, the more oxygen debt there is repaid. It removes CO2 by the plasma and carbohemoglobin. It maintains ventilation, circulation and body temperature. It needs 5 to 8 liters of oxygen and can take minutes up to hours. It removes or oxidizes lactic acid and replenishes muscle glycogen stores 2 hours to days. Carbon dioxide is removed in the lactic acid slow recovery system. 70% is carried into the plasma as carbonic acid. 23% is carried by hemoglobin as carbohemoglobin, and 3% is dissolved into the plasma. Lactic acid is removed or oxidized. 65% is converted into pyruvate and enters Krebs and is ultimately converted to CO2 and H2O. 5% of lactic acid is converted into glucose in the Cori cycle in the liver. 20% of lactic acid is converted into glycogen in the Cori cycle in the liver and stored in the muscles and liver. 10% of lactic acid is converted into protein.